Good morning. My name is Brian Clegg. I'm a science writer. The last 25 years, my day job has been writing books and articles on science for the general public. And I live in Swindon, so it's a great pleasure to, I think I've spoken now at every festival tomorrow so far. It's a great pleasure to come back and do that again. And today, what I'll be dealing with is interstellar tours. And what we're taking today is a slightly imaginary voyage through the galaxy on the Starship Endurance. The Starship obviously is fictional, and this, for the point of this talk, we're thinking of ourselves about 200 years into the future. There's one fictional bit of science which I'll mention when I get to it. Everything else I'll be covering is what we now know as our best science at the moment. There's a lot more in the book that accompanies this, but I'm going to, obviously can't do it all today. I'm going to pick out some of the best bits. Now, to get started on our voyage, to go around the universe, we actually need to get away from the Earth. And that's not trivial. It actually is quite difficult. I'm conscious that it's a little bit heavy on the lighting. I gather we can't, is it all or nothing, literally, with the lighting? Yeah, okay. So if you can't read anything, let me know, and we'll take the lights out and do it in the dark, but otherwise we'll stay as we are. Getting away from the Earth is not trivial at all. If you were a superhero and you got yourself a ball and threw it up into the air, in order to get it away from the Earth's gravity is so strong, you'd have to throw it at 11.2 kilometers per second. That's pretty fast. You can cheat a little bit. If you throw it in the direction that the Earth's rotating, you can reduce that to 10.8 kilometers per second, but it's still pretty hard to throw something that fast. Incidentally, one of the first science fiction books in the modern sense, Jules Verne's Voyage to the Moon, they did exactly this in his book. They basically put all their astronauts into a shell and fired it from a huge cannon called Columbiad. Now, the only problem with that is when you fire something out of a cannon, all the acceleration has to happen in the length of the barrel. And so before it leaves the barrel, it has to get up to that 10.8 kilometers per second, which basically means it would have to accelerate so quickly, all the astronauts would be squished into liquid. So it's not the ideal way to take off. We don't recommend that. But luckily, as you'll know, people have managed to get out into space. And the reason they can do that is we don't just throw them. They're under power as they take off, and as long as you've got your motors firing as you go, you can go as slow as you like, you can get away. You don't have to get up to the escape velocity, as it's known, to do that. But the trouble is you do need a lot of fuel to do that, which is why modern rockets, or late 21st century rockets, had the stages that fell away because they were carrying fuel to reduce the weight. There are alternatives available to us in the future. One that isn't available, sadly, is to beam up, as they did on Star Trek. They only did that, frankly, in Star Trek because it saved money on special effects. But there is a scientific thing you could do that kind of does this. There's something called quantum teleportation that does allow you to effectively set up a copy of atoms at a distance. But there are two problems with it. One is it's very slow, relatively speaking. You've got an awful lot of atoms in your body, and if you did do that, it'd take you millions of years to actually make the journey. The other problem is it literally does make a copy and destroy the original. So every time somebody on Star Trek gets in the transporter, they're actually destroyed, and a copy of them is made somewhere else. I don't know about you, but I'm not so enthusiastic about going traveling to be destroyed to be able to do it. Another thing you might see in science fiction, and to an extent in science, is something called a space elevator. In theory, it's a quite simple idea. So you get a satellite up in space that's going at the right height to go around at exactly the same rotation as the Earth, so it stays over the same point. We've got plenty of satellites doing that. Now, the thing with satellite orbits is the speed depends on the height, and to be able to do that, you have to be about 35,000 kilometers up. So here's your problem. If you want to build a space elevator, you've basically got to drop a cable 35,000 kilometers from the satellite to the Earth, and then you go up there in an elevator. Unfortunately, there is nothing in existence, not even graphene, the strongest thing we know, that could come anywhere near being strong enough to support its own weight if it was a 35,000 kilometer cable. It just isn't practical. It may eventually be possible on something about the size of the moon, but certainly nothing bigger. So unfortunately, that one's off as well. Also, incidentally, if you did have an elevator into space that way, it'd be quite slow, because remember, 35,000 kilometers, that's almost the distance around the Earth. So it would take it a little while to get up to the top there. In reality, a couple of hundred years in the future, where our endurance is built, we're talking about basically something quite similar to what we do now, but perhaps using different means of power. The Starship itself would stay in space. Anything big, it's much better to build it in space and never bring it down to the planet. So we can get up there. Once we do get up there, in principle, we're going to be weightless. And that's fun. It's nice to float around and do all those nice things. But there are some technical problems. It's not good for your health if you're out there for a while. So we're going on a long cruise. You're going to lose muscle strength. You're going to lose bone mass. But also just some of the basics of everyday life, many of which happen in a bathroom, are quite difficult with no gravity. So because of that, to make our passengers comfortable, we do need some artificial gravity. Thankfully, Albert Einstein realized that acceleration and gravity are effectively the same thing. So if you're accelerating, if you've ever been in a plane, as it takes off, you get pushed back into your seat. It's like a feeling of weight. It is effectively exactly the same thing. If you're accelerating, you will feel the effect of gravity. But you do need to be accelerating all the time. We can't carry enough fuel on the ship to accelerate all the time. So what we can do is spin you around, because actually being spun around is a form of acceleration. I don't know if you've ever been on one of these rides at fairs where basically you stand against the wall rotates, the floor drops, and you're pinned against the wall. It's great. There's no, you get a gravitational pull effectively to the outside. It does work because basically acceleration is a change of velocity, and that's both speed and direction. This is change of direction, so you've got some acceleration. That's great, but unfortunately, it also makes you sick. If you've ever been on one of those rides, if you stay on it too long, you start feeling pretty queasy. The last thing we want is a Starship full of sick people. Luckily, though, if the wheel's big enough, it doesn't matter. So if you have a nice big wheel, like the one they portrayed on the space station in 2001, A Space Odyssey, and incidentally, I confess we did actually nick the visual effect look of that poster for this book. It's great because you can produce a feeling of weight, but you can rotate slowly enough that you don't feel sick because you've got the dimensions of the thing to do it in. And that's fine for a space station, but we want something on our Starship. And in the film 2001, if anybody's old enough to see it, have seen it the first time or have ever seen it on video, they actually had a little rotating section in the middle of the ship. This is the actual, I don't know how well it shows, yeah, it's not too bad. The actual set from 2001, that is the rotating part. They basically rotated the cameras so it looked like the people were actually walking around upside down, all that kind of thing. That whole drum rotated, which was great until one of the engineers left a wrench on the set while it was rotating. They had a very important visitor called Marvin Minsky, who from the MIT, visiting them at the time. The wrench nearly hit him, and the poor engineer got fired for doing it. But anyway, it's a great set, but it's not big enough. To actually be effective, to get about 1G, the amount of gravity we feel on the Earth, your wheel needs to be about 500 meters across. You can get away with making it smaller, about half gravity. It's okay for most functions. You can get it out to 100 meters, but it's still a bit big for a ship. So I would suggest looking at alternatives in the future. There's one last thing we need to get over before we can get off into space, and that's going faster than light. Because if we're going to go anywhere in this galaxy, we need to get to the stars, and that means going faster than light because they're a long way away. Even if you just go at the speed of light, the nearest star to us, other than the sun, to take you more than 4 years to get to there. Now, the reality is we cannot go faster than light. In fiction, you'll find various things happening, and sometimes it's like playing with these things. So, for instance, Star Trek uses a warp drive, and there's a theoretical thing that is a bit like that in principle. But unfortunately, it requires a vast amount of negative energy. Negative energy does exist, but it's very difficult to make in very small amounts. So we're not quite sure how you would do that. The other problem with a warp drive is that you wouldn't be able to see outside, and you could still hit things. So it'd be a bit embarrassing. You're basically going blind through space, which would be a bit worrying. An alternative sometimes put forward is something called wormholes. You'll see this a lot in science fiction. Again, theoretically in physics, they could exist, but the fact is nobody's ever seen one. We don't know how to make one. If we did know how to make one and you tried to go through it, it would collapse, all the physics says. Wormholes, very unlikely, frankly, as a practical means. So for our purposes, I have had to invent a totally fictional hyperspace drive, a way of getting us elsewhere in the galaxy. This is the only bit of fiction in the science that you will see, but we need that to get away from the Earth and see what's around us. So it's time to set off. We're going to leave our solar system. You may be surprised to learn there isn't actually a sign out there saying that, and some people, if there had been one, would have passed it. The extent of the solar system is a bit vague. The usual measure is the solar wind, which is basically all the stuff that gets pumped up by the sun, pushes the material around the solar system away, and the edge of the solar system is usually thought to be where it stops doing that. And that's about 90 times the distance the Earth is from the sun. So once you get that kind of distance from the sun, the theory is you're out of the solar system. It has already happened by the start of the 21st century, and we're going to stop on our journey alongside one of the early probes that had already done that at this point. It's called Pioneer 11. It's out there now. It was launched back in 1973, quite small, weighs quite a lot less than a car, and we've lost contact with it for a long time now. And on the side of it, it has a plaque that is designed to communicate with aliens. And I thought it'd be quite fun, given that you probably understand people better than aliens would, just if you could quickly interpret for me what's on this plaque. Unfortunately, sometime in the 22nd century, it was hit by a meteorite, so it is slightly damaged, as you will see. But apart from that, we can get the basic feel of it. It's a piece of gold-plated aluminium. It's quite small, and it has these various inscriptions on it. Now, some things are fairly obvious, so hopefully you can work out that those are human beings, and this thing along the bottom is supposed to represent the solar system. Unfortunately, there are two things wrong with that. One is, of course, it has, on the end, it's got Pluto, which we don't recognize as a planet anymore. But the other problem with it is this is Pioneer 11, and that arrow shows the path of Pioneer 10, not Pioneer 11. So they got that wrong as well as far as Pioneer 11 is concerned. I'd also suggest, by the way, unless your aliens have ever invented bows and arrows, they will have no idea of what an arrow means. Why would they? Because they wouldn't have seen an arrow. But anyway, that's the easy bit. Well, I'll try you on a semi-easy bit. Anybody like to suggest to me why there's a picture of Pioneer 11 itself behind the people? Any thoughts as to why that might be the case?
Scale.
Sorry?
Scale.
Scale, thank you. Yeah, absolutely. So that's to scale. It shows you how big people are because you can see how big Pioneer 11 is. After that, it gets a lot harder. If you look up at the top left, we've got these two things look a bit like dials. If you look very closely, the top left one has something kind of pointing down, and the top right one, sorry, the right-hand one has something pointing up on the top of it. You are meant to deduce from that that this is referring to the hydrogen hyperfine transition. Obvious, isn't it? So basically, hydrogen, the element hydrogen, usually found in a molecule with two of them, can go through a transition where the spin of its electron around the outside flips from one direction to another. And that's what it's supposed to illustrate, because that gives us both a length and a work period of time. But how you're supposed to work that out, I have no idea. The line length in the middle is supposed to indicate that distance is 21 centimeters, which is the wavelength of the frequency of this transition. I'm already lost. I suspect our aliens would be as well. Let's try just one more thing. Over on the right here, there's this little marker. I'll just zoom in to have a look at that. This also is slightly damaged in the meteorite strike. There should be three identical vertical lines, not a broken one. Any idea what that's meant to say? Does that suggest anything to you at all? Does it help if I say it's a binary number? Anybody good on binary? Okay, this is the number 8, clearly, which is 1000 in binary. Again, how you're possibly supposed to work this out, I do not know. The idea is, remember we got that 21 centimetre distance. This is showing you the woman is 8 times 21 centimetres high, because if you look at the main picture, it's actually between those lines showing her height. Yes, no, was there over on the left here, one last thing, this starburst thing shows you where Earth is, sort of. The idea is that each of those lines points to a pulsar. So these are very rapidly rotating neutron stars. We'll come back to those a little later. And the numbers indicated by all the dots, the dashes on the line, which you're supposed to work out is binary, and there's a multiple of the 0.7 nanoseconds that flip takes, tells you how frequent they are. I don't think anybody's going to find us. It's probably even less likely because one of them's actually wrong. But some people actually would argue that it's not a bad thing. Stephen Hawking, the late Stephen Hawking, did think it wasn't a good idea for aliens to find us, because chances are they wouldn't be friendly, so we don't particularly want them to find us. But actually, it's certainly not going to help. In the main tour, so remember we're doing a condensed version here on the tour in the book. I've taken a few other of the probes that are out there, have a look at them as we pass. But I think it's time to go and see something a bit more dramatic. So we're going out about 1,500 light years. A light year is 9.46 trillion kilometers roughly, so it's quite a distance. And we're going to a location in Orion. This is the constellation of Orion as you see it from Earth. Hopefully you can just about see it. I think it's the most recognizable constellation in the sky. Many of us will have seen it. It's visible all over the world at some time during the year. I saw it quite recently here, so you should be able to see it on a clear night. Just worth emphasizing, I'm sure most of you know, but the stars in a constellation are not connected in any way. It's just a visual image to spot things, but there is no connection between them. So for instance, Alnilam, which is the star in the middle of the belt of 3 there, it's about 1,300 light years away, where Bellatrix, that one there, is only 245 light years. They're very different distances from us. There's no connection between them. But down at the bottom here, underneath the belt, before you get to the bottom stars, there are 3 roughly vertical stars, or parent stars, and the middle one is what's called a nebula, which is comes from the word Latin for fog or mist. It's about 1,500 light years away, and it's a nursery where new stars are born. So we're just going to take a visit out there. It's been noticed for quite a while. It's slightly surprising. It's only as recent as 1610, I think, because it's actually fairly obvious. And when you get closer to it, it looks a bit like this. This is the real-time view from our Starship, but we've changed infrared into visible to make it that a bit clearer. Quite dramatic looking. There are some young, newly formed stars out there. There's 3 in a line there. It's no connection to the belt. Remember, this is just a fuzzy little patch down at the bottom. But these are stars that are just coming into existence. They're being born. The whole thing is about 20 light years across. And it's got well over 1,000 stars coming into existence there at the moment, or rather 1,500 years ago, because we're seeing it as it was 1,500 years ago, because that's how long it takes light to get to us from it. It's part of a huge complex, as it's known, of molecular clouds. That's gas and dust that's actually bigger in scale than the whole of the Orion constellation as seen from us. But this is where it's really concentrated, going on formations of stars. And what's happening is hydrogen, various other things, but mostly hydrogen is being pulled together by gradually, slowly, over time. It takes a long time. And eventually what you'll find happened is that hydrogen gets compressed together by gravity so much that nuclear fusion starts. It starts generating energy. You've got a solar system in the making. And what we're seeing here is one that's just beginning. So in the middle, you have already got that star, and around it, you've got what's called a protoplanetary disk. So that's stuff, gas, dust, that is being pulled by the star around it. And it is in that shape because it's spinning. Spinning is incredibly important. Practically everything in the universe spins, basically because it's not evenly distributed. So as it comes together, it will tend to move one way or the other. And what you get is kind of a pizza dough effect. So if you've ever seen anybody making a pizza from scratch, you start with a ball of dough, you spin the ball, and it comes out into a disc because there's force pulling it together, but there's nothing affecting it that way. And the result of that is you end up with a disc around it, and exactly the same thing happens with the stuff around the star. As it spins around, it forms a flattish disk. Now inside, there's a lot of heat, there's a lot of energy stuff coming out of that new star. Typically, what you'll find happens is relatively small rocky planets form there because there's so much pressure it pushes away gas. Further out, the gas can come together itself to form kind of mini stars, and that's exactly what our solar system is like. So we've got rocky planets like the Earth near the sun, we've got gas and ice planets further out. It's not always like that. It depends how it started. It depends how the whole thing started, but that's basically what's happening of a solar system coming together, and planets are beginning to form. I don't really have time, unfortunately, today to visit a planet. We do look at several in the book, but what I would like to do instead is to move a little bit in Orion, remember, to a totally different place, actually, because the things aren't connected, to see something very interesting happen. So just having a look back at Orion, does anybody know their astronomy and can tell me what the top left bright star of Orion's called? Pardon? Yeah, so Betelgeuse, Betelgeuse, however you want to pronounce it, it's that one. It is one of the few stars that is absolutely clearly has a colour that's, in this case, red. It's technically called Alpha Orionis, but everybody tends to know it as Betelgeuse or Betelgeuse. It's about 500 light years away, just a bit more. Originally, like many of the well-known stars, the big stars, the name was Arabic, and excuse my attempt at the pronunciation, but it was something like Yad al-Gawza. And it was actually written down wrong. Somebody transliterated it wrong and wrote it down as Bad al-Gawza instead. So Bad al-Gawza became Betelgeuse, whatever, however you want to pronounce it. Let's just have a look at it for real. And it doesn't look like your typical star because it's going to go supernova. Now, I ought to throw in what I call a speculation alert at this point. In terms of now, in terms of the 21st century, we think it's going to go supernova sometime in the next 100,000 years. We don't know for sure. For the purposes of our tour, we just happen to have turned up just before it's going to go supernova conveniently. So we can find out a little bit about that. And it's going to be what's called a type 2p, come back to that in a moment, supernova, which means the inside bit of it is going to collapse to form a neutron star. Originally, the word nova just means new in Latin. It was just anything that appeared in the sky that you hadn't seen before was a nova. But supernovas are a totally dramatic, catastrophic effect where a star is either totally destroyed or more likely mostly destroyed, leaving a remnant. There are various different times, depending upon how much hydrogen it is, how big it is, that kind of thing. Okay, so we actually just have to go out to the star itself just to see it in its last moments, because we believe it is about to go. So we'll just allow that to happen. Unfortunately, because you can't hear anything, because in space, nobody can hear you explode. That's for the old ones who remember Alien. So we expect this to happen at some point relatively soon in terms of the timescales of the universe. Now, Betelgeuse was a red supergiant, about 15 times as heavy as the sun. To become a supernova, the star has to be big. The sun will never go supernova, it's not big enough. And what's happened here is, remember, they're powered by fusion, which means atoms coming together to form heavier atoms. Well, ions strictly. And this has started in hydrogen, gone to helium, gone on as far as it can go to iron. And the trouble is, once you've got iron, it doesn't give out energy when it fuses. You have to put energy in. It can't go any further. It runs out of oomph. It's not got enough fuel to keep going. Because of that, the core of it has collapsed together, and its gravitational pull was strong enough that it's collapsed as a set of neutrons. Now, those don't repel each other like normal charged matter, and because of that, they become very massive in a very small size. So the core of this that's left, the neutron star, is about 20 kilometers across, and it has the mass of 1 to 2 times the mass of our sun. To give a feel for that, if you had a bit of neutron star in a teaspoon, it would weigh about 100 million tons. That is pretty heavy stuff. Another thing, if you could stand on a neutron star, which obviously you can't, but if you did and drop something from 1 meter above the floor, it would accelerate so fast under the gravity that it would be going 1,930 kilometers per second by the time it hit the ground. Neutron stars, gravity is very strong. And what happens is, I don't know if you saw, when it exploded, there was kind of a ring of explosion. And as that happened, the core, the central part, then is pushed together and then bounces back. And that produces a vast amount of energy. And that's where all the atoms, well, almost all the atoms, that are heavier than iron come from. So we have lots of atoms in us heavier than iron. They aren't the main things in us, but we do have plenty of them in there we need for life. They would not exist were it not for supernovas. That's supernovas and actually colliding black holes and things like that. The only kind of sources that you can get for this more massive stuff. Without it, we would not exist. So we can't actually wait for this to happen, but this is the remains of a very similar supernova to Betelgeuse. It's called the Crab Nebula. It's the same type of supernova, a bit further away from Earth, in fact, 6,500 light years. And it's now about 11 light years across, so it's taken a while to get to this stage. This is all the stuff that's left around the outside. The neutron star is not visible. It's there. It will be there in the middle. And that's fine with this kind of size star. But if you get a big enough star, there's not enough resistance to collapse, even for a neutron star to form. It'll just get smaller and smaller and smaller, effectively get to nothing at all. And the result then is a black hole. Nothing can get out of a black hole, not even light, hence the name. And we're going to visit the first one that was ever found. It's about 6,100 light years from Earth. And you might be a little bit surprised to see it in the sense that it certainly doesn't look very black as black holes go. That's because there are actually two stars here. We're familiar with having like one star in the solar system, but actually there are often two stars in a system. Here, the thing on the left is a blue supergiant, a big star. The thing on the right is the black hole, and the actual black hole is just a little black dot in the middle. And what it's doing is pulling stuff off the other star, because when it became a black hole, it disrupted the system sufficiently that the two stars moved together a long way, and now the two stars are only about half the distance of Mercury from the Sun apart from each other. That's very close, close enough for it to pull stuff off it. But you ought to stress that unlike what you see in the films and all that kind of stuff, black holes are not like something that pull anything in every way. You know, if you orbited a black hole at the distance you would orbit the star before it became a black hole, you can orbit it quite happily, quite normally. It's not a problem. The problem is that you can get as close as you like, so the gravitational pull gets stronger and stronger and stronger as you get close to it. And if you get close enough, you're going to end up being spaghettified, and this is a genuine scientific term. And what it refers to, if you imagine kind of falling into a black hole feet first, your feet are feeling a stronger gravitational pull than your head because they're further towards it than your head is. And just that small distance is enough to make a huge difference to the amount of pull. In this particular case, if you were 10 kilometers away from it, then the difference in pull between your feet and your head would be like the strength of a passenger train. So basically imagine your feet are fixed to a wall, your head is attached to a passenger train, and it sets off. That's what it would feel like. So do not do this. I do not recommend doing this in your spare time. The bright stuff around it is its accretion disk. It's a bit like a protoplanetary disk, so it's stuff that's being accumulated by it. It's all spinning, which is why it's in a flat disk. It's lit up basically because it's so hot, because it's being rotated very quickly. Things are bashing into each other, and it's getting very hot. Because of the effects of general relativity, the closer you get to it, the more space and time are twisted and warped. And in fact, from our viewpoint, what's happening near it will seem to be running very, very slowly. If you were there, it would seem just normal. But from our distance, looking at it from a distance, things will appear to get slower and slower. Light just doesn't behave the way we expect it to do. We got rid of all the rest of the material just to see the black hole itself and the material around it. And it would typically look around like this, where that top ring you saw was actually just the backside of the disk, but the light is being twisted so much as we look around it that it looks like it's not a disk. It looks like that strange shape with a curve. It's not really like that. That's just how the light is being twisted. And for that matter, the stuff isn't different coloured particularly. The colour differences are due to the Doppler effect. So I don't even know the Doppler effect with sound. If something moves towards you, the pitch rises. If something moves away from you, the pitch goes down, like when a fire engine goes past. It's the same with light. If it's moving towards you, the energy increases effectively, so it goes up towards the blue end of the spectrum. If it's going away from you, it gets to a redshift, and that's why you've got the difference in colour there. We're just going to look at one last black hole, one called Sagittarius A star, and that's the one that's at the centre of our galaxy. It's about 4.3 million times the mass of the Sun. We're talking something pretty big. This was the first view that was ever seen of it back in 2020s. That's actually using radio source. And out of interest, the name, incidentally, A just means it's the brightest radio source in the constellation Sagittarius, as seen from Earth. And star just means, well, it's interesting. It has no specific meaning at all. It just means oh, this is interesting. It has just like an ordinary star has planets going around it, this thing has stars going around it. There are at least 60. This is an actual view of them, of some of them. It's a repeating pattern, but they're orbiting around there, and these are all stars going around the black hole. You can't see much of the black hole itself. As far as we know, pretty well every galaxy has a black hole at the centre, and there's a bit of a chicken and egg thing as to did the black hole help the galaxy form, did the galaxy help the black hole form? The general feeling these days seems to be that actually is a bit of both. They depend on each other. So black holes help galaxies form, then that helps the black hole to get bigger. This is best approximation to what Sagittarius A star currently looks like. There's a bit of an accretion disk, a bit of stuff around it, but over the time it's been there, it's mostly cleared. I don't have time now, but in the book we go into things like pulsars and black hole collisions. But what I want to do is take a step back from our galaxy, going to the farthest distance our tour can take us to see the galaxy as a whole. Now this is what it looks like from Earth. You often can't see it like that, and it is quite an enhanced photo, frankly. Although actually, yeah, you probably are seeing it quite realistically. If you look on my screen where it shows the original photo, you can see vast numbers of stars. That's probably more like what it would typically look like if you saw it from Earth. It does need to be dark. So I've never seen it in Swindon. You have to go somewhere that's pretty dark to be able to see it. And if we take a look, not from Earth, but from the outside, the Milky Way looks like this. This was a 2020 simulation, and it's pretty much, we hope, accurate. In the universe itself, there are about 200 billion galaxies, so we're just 1 in 200 billion of that or so. The Milky Way itself has around 100 billion stars in it. It's a medium to large size galaxy. It's about 90,000 light years across, but only about 1,000 light years thick. So like everything else that spins, it's formed a disk. And we are approximately there in the Earth. Interestingly, the galaxy is old. The universe itself, we think, is about 13.8 billion years old, and this galaxy started to form about 13.5 billion years ago. So it's been there for most of the existence of the universe, although it was very different in the early days. Now, in the main tour, I'm going to also take in some dark matter. Again, don't quite have time for that today, because we need to get back home. I can't really leave you out in space, or you won't be able to see the rest of the show today. But as we come back, I just want to pause briefly. We got back to the solar system, but just outside the orbit of Neptune, where the Voyager 1 probe ended up in 1990. And the reason for this is that an astronomer and science popularizer called Carl Sagan suggested to the people who were operating it, why don't you turn it around, look back, and see if you can take a picture of Earth from out there. They didn't like it, actually. NASA was very doubtful about it because they thought it might damage the camera because it would be pointing effectively towards the sun. But they had a go, and this is basically how it came out. That little dot there is the Earth as seen from outside the orbit of Neptune. Incidentally, those rays are fake, as it were. They're not real thing. It's just sunlight getting into the camera. It's not a real entity, so we're just replicating that here. On the way back in, it would be nice to look at some other places, and again, I've done that in the book, But just to get this in the time, I'm going to skip that. But I do want to point out, before we get home, there was one potential problem. Having been on this amazing voyage, the Earth might not be there anymore. Because the reality is that we can only predict exactly what two bodies interacting gravitationally will do forever. Any more than two, even Newton worked this out, it's not possible. You can't 100% accurately predict what will happen with just three things in space. And obviously there are more than three things in the solar system. We don't know exactly what will happen to it in the future. And we think that sometime in the next few billion years, Mercury has a 1% chance of basically shooting off, hitting Venus and bouncing off like something on a pool table. So it's just potentially possible. Of course, the Earth might not actually be there anymore. So fingers crossed. But yes, luckily, it was there when we got back. Realistically, there is no chance, totally zero, really, of Earth disappearing any time in the next few billion years. So unless you are thinking to live longer than a few billion years, you should be okay. I won't worry about that. So Earth, I just want to very briefly say one thing about Earth, that it's special. It might seem tiny. Remember, there were hundreds of billions of galaxies. Our galaxy with billions of stars in it. We're just one star, one planet around that star. But actually, Earth is a very special place. Planets like Earth, when we started, because we've now, even sort of at the start of the 21st century, we discovered about 5,000 or more planets around other stars. Earth is rare. There are various things about it that are special. Firstly, it's in what's known as the Goldilocks zone. So it's not too hot, not too cold, just about right, which means it's the right distance from the sun to have water liquid. As far as we're aware, you need liquid water for life. So it's got that going for it. One of our most important things is the moon. The moon is very special. Very few planets have a moon so big compared to the planet. And as a result of that, it has stabilized the Earth's orbit considerably, and it's also influenced the way the Earth formed. And our plate tectonics, the way that the surface plates of the Earth move, is actually really important for the carbon cycle that means we do have liquid water. And that was influenced by the moon's formation. So basically another planet hit the Earth, blasted off part of the Earth and part of the other planet to form the moon. And in doing that, that's effectively started the process that we have, that, say, Mars doesn't. And because of that, we are much more likely to have liquid water. We have a relatively stable star. So when we look out at a lot of other planets that potentially could have life, the star actually is much more variable in the amount of stuff it throws out, the radiation it produces. And we also have a very strong magnetic field, which pushes away the stellar charged particles that come in towards us. Mars doesn't have that. And because of that, if we ever do go and live on Mars, chances are we'll have to live underground, because the radiation on the surface is too strong to live for long with. On the Earth, we're fine because we have this magnetic field. So we've got a lot of things going for us. And I don't know about you, but I certainly regard it as a very special place. And I hope we can continue to look after it and make sure it is. So that's been a high-speed tour through this. Just check time. Okay, we've got just got a few minutes for questions, if you have any. I'll also be here after, at the end. We've got a few copies of the book. Unfortunately, the bookshop hadn't had delivery until the last minute, and they may not be here today. So I do have some copies of the book associated with this, and a few of my others if you want to have a look afterwards. But also, if you have a question and don't want to answer it, ask it in front of everybody else, please do come and see me. I promise I won't make you buy a book, but I would love to have a chat. But thank you very much for listening. Are there any questions? Yes, sir. Right, can you just wait till we get the microphone and everybody can hear.
Wasn't our galaxy going to collide with the Andromeda galaxy or something? Like, what would happen if that happened?
It is going to happen.
Oh, it is. Okay.
So Andromeda is the nearest big galaxy to us. We say near, but it is 2.5 million light years away. They are coming together. So basically, the universe is expanding. Most galaxies are moving away from us as the universe expands. Andromeda is so close, relatively speaking, that the gravitational pull between the galaxies is pulling them together. We will collide to form a new galaxy, But we're talking, not millions of years, but at least 1 billion years away. So again, not something to really worry about at the moment. It could have catastrophic effects. It could have very little effect, depending on how they merge in a particular region. The idea, they'll probably end up as a huge galaxy of the combination of the two, but we're looking a long way into the future before that's going to happen.
What do you think of the existence of white holes?
Okay, so white holes, black holes we've already seen there. We know something that behaves pretty much like a black hole exists. We've never actually been to one, of course, and chances are realistically, we probably never will get very close to one. But as far as we can tell, they're certainly behaving as if they were black holes. A black hole basically goes to nothing and everything gets into it. A white hole is a theoretical concept that is the opposite. So basically everything comes out of it. And if, when the universe started, the so-called singularity at the start where everything was together, the suggestion it has been sometimes that could be considered as a white hole. There may be white holes, but frankly, I don't think there is no evidence as yet of anybody seeing anything that could be a white hole, put it that way. And in some ways, a white hole should be a lot more obvious than a black hole, because stuff's coming out of them rather than going into them. They're interesting to play with. It's kind of thing, theoretical physicists love playing with ideas, but as yet, there is no concrete evidence for their existence. I would say both white holes and black holes break physics as we now understand it. There has to be something else, some other physics we haven't worked out yet, to explain what happens, because they both have things that go to infinity. And as soon as you get infinity in your maths, you know there's something going wrong with the physics, and it needs fixing. Simple answer is, I don't think that we are going to discover them, but they're fun to play with as a concept.
How does a black hole get created?
Okay, so it's a bit like what I described with when Betelgeuse exploded. It's basically, but this is a much bigger star. So again, it's run out of stuff in the middle that will can merge together, get more and more massive, generating energy, and it starts to collapse because there's nothing puffing up the star, because normally the energy in the middle pushes it outwards against the gravity pulling it in. Once that stops, gravity starts pulling it all together. And as the star's really big, there's so much gravity that things get squashed smaller and smaller and smaller together until it becomes a black hole, because it's so strong a pull, nothing can resist it. That's how we think black holes form. It's just possible some might have formed in the early universe when everything was weird and wonderful and things were exploding all over, whatever, something might have just compressed enough. But mostly it's old stars, very big stars that collapse, and all their stuff, all that's left in the middle, they'll still blow a lot off of the outside, but a lot that's left in the middle has collapsed into something that's effectively no size at all. And that's a black hole forming. Okay. Any more? Have I stunned you into silence? Was that a possible or just a stretch? Anything? Anyone? No? Yeah.
We speak about interplanetary commercial travel, right? When do you see that commercially viable? Because like SpaceX, everybody's trying to, take humanity to different planets. Mm-hmm. But when do you see that commercially viable, like 100 years from now, for example?
Okay, so we talk about commercial viability of interplanetary travel. This is very much within the solar system, realistically. So what we've been talking about today, the fictional part, was being able to travel faster than light and get out there to vast distances. Within the solar system, obviously, we've already sent probes to Mars. We've had people on the moon. We haven't done much of it. If you think, the last time somebody was on the moon, I think was about 1972. So what we're talking about 50 odd years ago. It's not something that's easily done. And even with the new technology, with things like SpaceX, finding ways to do things differently, it's not going to be easy. I think the majority of people who think you're going to make money out of say, mining asteroids or something like that, chances are you have to go a long way down the line before that becomes realistic. But I think certainly within the next 30, 40 years, we will have people on Mars. Whether it be financially viable at that stage, I think is pretty doubtful as a way of making money. But as you say, I think circa 100 years timescale feels about right for actually it becoming a commercial proposition that you might get some good stuff out there that is so good it's worth spending all that money to get, say, a mining thing out there, or low gravity. Actually, stuff around the Earth is a lot cheaper, of course, so that continues to be a good place, and potentially financially you can make things out of that. Okay. Yep.
Is there any viable evidence of life on other planets, or life on other planets coming to our planets, or travelling around the universe?
Okay, the quick answer is not yet. There are two things. In terms of life, until very, very recently, we thought the most likely life other than on Earth was on somewhere like Titan, one of the moons of, my brain's gone blank, Saturn, where there's an ocean effectively under ice and liquid water. And it was thought for a long time that there may be, probably just like bacteria, but very basic life happening there. Very recent, I think in the last week, they've announced that it's less likely than we thought, because if there were, you'd expect basically when something hits it and actually material comes out from the ocean, you'd expect to see carbon type stuff or something like that, because as far as we're aware, carbon is the only sensible basis for life. And there just has not been enough. I think they've described it as like sort of one elephant's worth of carbon in the whole planet and the whole moon. So chances are getting less in terms of the solar system of ever finding anything there. Further out, it seems in some ways pretty unlikely that there isn't somewhere a planet where life has started. Earth genuinely is very special. There are lots and lots of planets where it definitely will never start. But the potential is there for other planets. You then got, an extra step to get higher forms of life, not just stuff like bacteria, an extra step to get intelligent life, and an extra step to get intelligent life that can travel. And if they did, chances are, just like us, it's only going to be within their solar system. Interstellar travel, as I say, at the moment, we've had to rely on science fiction to get us out there. So until we can find a way to do that, or somebody can, chances are, even if they are out there, we will never meet them. We might be able to exchange very slow radio messages, bearing in mind radio travels at the speed of light. So the nearest star, it takes 4 years to get a message to them and 4 years to get a message back. And that star is very unlikely actually to have life on its planets, or stars actually, it's a 3-star system. So there probably is something out there, but the chances of coming across it is very needle in a haystack. I think it's highly unlikely. I certainly don't think UFOs are in any way connected to life from other planets. Or UAPs, we have to call them now, unidentified aerial phenomena. Any more, or are we there? Okay, well, thank you very much. I hope you found it interesting. As I said, please do speak to me on the way out if there's anything else you want to ask about. Have a look at the books, and thank you for your time.